So I'm Heather Beadle, and this is one of my AAPG Distinguished Lectures for the 25-26 school year. And today I'm going to be talking about characterizing subsurface systems for energy and sustainability applications, going over some of the attributes and machine learning algorithms that my research group at the University of Oklahoma, the AASPI research group, has found incredibly useful in our studies. So my goal for this is that by the end of this talk, you are so inspired to run back to your computers and try out a new attribute or two, and maybe also explore combining some of them with a machine learning algorithm. So let's get started. As we know, the world needs more energy. This is something I've been thinking about for years. Probably many of you have too. And if we look at this energy consumption by source for global, you can see that there's been a lot of uptake in all different types of energy types. And this is because we've got huge amounts of population and economic growth all around the world. We have also been electrifying some of our more traditional hydrocarbon sectors, so an easy one to think about is cars. There's also been a lot of digitalization, and the creation of data centers require much energy. And also there's been standards of living improvements all over the world. So in many, many countries, more and more people are being able to use, say, air conditioning, which we all know is a huge driver of energy. So when we look at the different sources, kind of breaking it down, we can see that with the other renewables, which I've highlighted here kind of more in the maroon, this might be some we're interested in as geologists, things like geothermal. And then also, as we look at the different energy consumption by source for some of the larger energy consuming countries, you can notice that a lot of our energy comes in the form of coal, oil, and gas. And so this means we are putting some extra carbon into our atmosphere. And so carbon capture, whether storing or utilizing carbon that we capture in the subsurface, is another area where geoscientists like myself have been focusing more recently in the last decade and two. So the good thing is that many of the methods we've developed as geoscientists for traditional hydrocarbon exploration are excellent for the energy addition or energy expansion and sustainability focuses that we have going on now. And so I'm going to talk about, I just selected some of my favorite attributes, some of the ones that my students and research group have been using a lot. And so I'm going to start off by kind of talking through some of those, from coherence and curvature, some of the old goodies that are great for edge detection, to aberrancy, multispectral attributes. I'm going to talk about the shape index, GLCM texture, and a newer old attribute called distance quadrant. So first, let's get going with what is a seismic attribute. But before we even get to that, just in case I have any folks that are new to seismic reflection data, I just want to do a quick reminder that the basics of seismic reflection is pretty straightforward. A lot of us learned it back in our physics classes in high school or college, where you're sending energy into a container. And depending on the properties of the materials that it is interacting with, that energy will reflect or transmit. Sometimes it kind of changes direction or that angle of bounce. If you've ever put a straw or a pencil into a cup of water, I remember this is what I did at my college. The pencil looked like it was bent, but it wasn't actually bent. It was just the light reflecting. And so it's the same properties for the interior of the Earth. And what we end up getting after all of the collection of data is an image like we have here over on the right-hand side. And let me turn on my laser pointer right here, where what we're seeing is not the layers of the Earth, but rather the interfaces between the layers. So you can see how it's bounced over here. Well, now we're seeing those interfaces. And as a trained geologist, you might be able to pick up on a lot of different features from these discontinuities, which are faults in this case. And there's also a lot of variation from the amplitude, so how bright those reflections appear. So they're brighter here, dimmer here. There's changes in frequency. And so all of this is what we're looking at with seismic attributes. And so the reason we use seismic attributes is because they help us see more. they help us kind of see those patterns that we as geologists would recognize as something being geological in nature. So in this case, on the left-hand side, I'm using a edge detector coherence and also amplifying, in a sense, the energy, so the amplitude. And that lets me pick up a lot of really interesting patterns that, knowing about the geologic setting, I can then interpret. And what I want to say here is that attributes are just math. We're not doing any magic in these cases. A lot of times we're just trying to hone in on those parts of the seismic wiggle trace that we're interested in and that give us that geologic information we're looking for. And so I've mentioned that they're very, very useful in enhancing some subtle features, and I'll show you attributes in particular in a minute or two. And we like these because they help us visually identify geologic structures and stratigraphic features that we may be interested in. They can also assist in reservoir characterization, whether you're doing it for traditional hydrocarbon exploration or for understanding a reservoir for geothermal or perhaps carbon capture storage or EOR purposes. And then they also improve the accuracy and confidence that we have in our interpretation, so in our mapping and what we understand of the subsurface. So they let you see the data in different ways so that you can kind of put that geologic story together and be confident in it. So let's get started. All right, so the first thing I always like to mention is that you must always account for reflector dip when calculating any geometric attribute. And it can be shown really easy in this diagram where you can see we have in green a dipping reflector. Okay, so an interface that has a dip to it. And if we don't use the right dip, which in this case would be 5 degrees, what we're going to end up doing is kind of smearing information in our geometric attributes from above and below that interface. And so dip is always the first thing we calculate. Anybody in my group calculates. You can calculate the dip azimuth and then also the dip magnitude. And so now for every geometric attribute we calculate after that, we are calculating all the other geometric attributes along this green line, so along the coherent dip. So my favorite attribute for all time, it's coherence. So coherence is a great edge detector. And what it does, and there are a dozen different ways to calculate this, and I'm trying to keep it really straightforward today, is you can compare one of your traces, so in this case the trace in pink, with its neighbors. So whether you're working in the cross-line direction or the in-line direction, you may be comparing it to 3 neighbors in each direction. You may be calculating it over a square or over a circle, like a radius, away from that particular wiggle trace of interest. And it can work in different ways. So besides whether you're looking 4 milliseconds above and below, or how many neighbors you're looking at, you may also be focusing more on the shape of it or the amplitude of it. And so in this case, the example of coherence I'm showing here is where you're taking the energy of the average traces. So that would be this pink line or this pink wiggle right here over the average energy of all of the input traces. So that would be the red ones. All right. But the whole point is just, to compare one waveform to its neighbors, whether you're doing it by shape and or amplitude, and that gives you edge detection. And so this is an example. I'll show a couple examples from the Great South Basin of New Zealand area. At this time slice, we have a lot of faults, and so coherence usually just takes a few minutes for most computers to run, and you can see here that it's very easy to pick out some discontinuities, some faults that are occurring in this area. So the next attribute I want to talk about is curvature, and curvature just helps delineate some very subtle curves that can often be overlooked by coherence and dip. You can have your structural most positive curvature, which delineates ridges or anticlines, or your structural most negative curvature, which highlights synclines or valley features. So one thing to notice in this amazing picture is that if you have dipping planes or flat planes, they have no curvature. So really we're just getting a sense of the curvedness of that seismic horizon. When we look at the same time slice right here, you can see that we are picking up some of the most positive and most negative aspects on either side of a fault. Sometimes you have a little bit of curvedness as that horizon that you're mapping is kind of looking like it has a little upthrown and downthrown curvedness. And I'll show an example of that in a minute. But so you can see we're getting a lot more features. There is a little bit more going on than we were able to pick up in coherence up here on the upper right-hand side. The next attribute, which kind of goes in line with dip, curvature, and coherence, is aberrancy. And so when we look at how these attributes work, with coherence, we're able to really image it the best when we have very clear fault offset. For curvature, like I mentioned before, sometimes you've got that curvedness of the seismic horizon, you know, how it looks in the seismic data. So you're kind of picking up a little bit of syncline and anticline with the curvature. And if you're below resolution, like we are down here in the lower left-hand side, you often don't see coherence, but rather just the curvature. And where we've gotten into aberrancy is down here in this region where you've got fault offset that's below resolution. So you're getting into perhaps, we've been using it in the basement areas, but you can see we've got a little bit of curvature that's picked up, and then also aberrancy is picking up right between it. So when we look at how that looks compared to coherence, I'm going to start here with coherence. So it's the same image we looked at before, nice clear faults. You know, up here curvature showed us a little bit more. And let's focus in on these two arrows. And when we look at aberrancy, again, this is calculated the total aberrancy and then the magnitude of it and the direction of it. So you can see that where we had that clear-cut offset before by that yellow line in coherence, it's not really picking up anything, but we are getting a lot of perhaps smaller scale faults, below resolution faults, being picked up in this area where curvature had started showing us that there could be something going on. All right, so now I want to talk about multispectral geometric attributes, which we've been using more and more at the last maybe 4 or 5 years in my research group. And so these work very similarly to spectral decomposition, if you're familiar with that, where you take your broadband seismic data and you break it down into your spectral voices, or just you know, around certain frequencies. And I'm going to show you an example. And so right here on the left-hand side, we've got coherence. And if we look at these 3 different sections, okay, so here the upper section, we can clearly see there's a fault in the vertical section, and we pick it up in coherence. Down below, coherence is picking up that fault, but in the middle, there's a gap. So you can see how if you were picking along this horizon, you wouldn't get that clear offset. So here's another example. Here we've got our full bandwidth data, and down below we've got our full bandwidth coherence. So as we're kind of picking along, you can see we've picked out this red line up here, and we can see as interpreters kind of looking above and below that there is an offset, and we would put a fault there, but coherence can't. And so when we're using coherence perhaps in a machine learning algorithm to do some auto picking of faults for us, this is really important that we've got to solve this problem. So we've got a gap there. You can see coherence picked up a gap here. As we move down and pick a few more lines, you can see that there's some areas where there is a gap that we would see as humans, but the machine, the algorithm, can't see it very well. But if we pick out particular spectral voices, so here we're looking at the spectral voice around 36 hertz, so no longer the full bandwidth data. We can note that coherence around that 36 hertz is doing a much better job. So it's much more continuous where we would pick it to be continuous. And then here at 55 hertz, again, we've got more continuity in the edge detector, the coherence volume, around 55 hertz. So this is just a quick example of the importance of thinking about using some of your geometric attributes in different spectral voices to really narrow down and focus on that geometric feature you're trying to pick, in this case faults. So there's different ways that you can pull this data together. So here we're using an RGB blending method, just like we would for spectral decomposition for stratigraphic features. And so we've got our input data. Here you can see the broadband data on the right-hand side. So this is looking at some channels and karstic systems in the Tarim Basin of China. When we look at different and pick out different spectral voices here around 18 hertz, you can see nice clear continuities of these channels and cavern systems. Around 25 hertz, some parts of it down here on the southern side show up a little bit better. And then here at 38 hertz. So we can assign them red, green, and blue and get a nice composite image of the system like I'm showing here. You can also perform multispectral analysis with more than 3 components. And so in this case, I'm showing an example where 6 different components were picked out. Here we've got a channelized system, and you can see that in certain areas you can pick out features a little bit better, like this kind of abandoned channel shows up better in a few cases. And so when you're doing this, what you have to do is you have to sum the individual components and weight them by the strength of each individual component. So it's kind of an extra step that we have added in order to more mathematically combine them rather than the visual red, green, blue method. And so to look at this kind of blown in a little bit more in a bigger picture so you could see it on your screens, here we've got our original broadband seismic data, and this is before structure-oriented filtering. Now when we look at the multispectral coherence, in this case the voices were chosen using exponentially spaced components. You can see that there's quite a few more features that are showing up very clearly here. Actually, let me go back. So I'll just toggle between the two of them because that's always fun to do. So we've got the original broadband and then the combination of 6 different voices. So original and combination. And so hopefully that shows you how just using one attribute, you can break it down into spectral voices and then recombine it to get more information out about your subsurface system. All right, the shape index is an attribute I wanted to talk about because I don't see many people using it very much. And the shape index is just a combination of different K1 and K2 curvatures. So you can see I've got the equation here, S is the shape index. And to break it down, when you calculate the shape index, it is a bowl if it is around 1, and so you've got this bowl shape. You've got a valley shape. You can also see saddle features, ridges, and domes. And so this can be really great visually. So to show you an example of this, here's the shape index in action. So this is in that same Great South Basin data set, a little bit deeper than the faults I've been showing you before. Here we've got seniorisis. And so now using the shape index, you can see here the red colors are these domes, and then the blue colors are the bowls that are associated with seniorisis. And what's great about this is you can apply different opacity, bring out different features. So in this case, we're trying to bring out more of the bowl shape, and you can even create geobodies if you need to. All right, so GLCM texture attributes are another great attribute that we've been finding very useful in machine learning applications for subsurface characterization. The 1-minute description of them, the way I like to think about it just to get started is it's a texture. So Kurt Marfert, he likes to describe it with different wood grains. So you've got your oak and your cherry and your maple woods, and they all have different textures to them. So you see different grain patterns in the wood. I like to also explain it thinking about fabric. So If you can imagine like taking your thumb, and your thumb is kind of the sensor or the statistical box that we're going to be using to calculate GLCM, and you kind of like rub it on. I've got a cotton shirt on right now, so I can feel something different than if I rub it on my keyboard, and so that's kind of a texture. So the way it works is you are statistically trying to represent lateral and vertical variability. And so in this case, I'm trying to show on the right-hand side, we've got our little 5x5 box where we're looking at different levels, different gray levels, and we're combining them in different statistical methods, statistical algorithms to try to understand the variability. And so we'll calculate it in different directions, we'll move it through our seismic section, and then recalculate it. And so in this case, we're looking at GLCM contrast, GLCM correlation, GLCM energy, and homogeneity. So they're kind of trying to give us information about how much variation there is in this 5x5 box. So it's giving us a texture of values. And so just to show an example of what this looks like in seismic, here we've got our GLCM homogeneity. So again, same area before where we saw the synuresis for the shape index. You can see we've got a very homogeneous shelf on the left-hand side, and then we've got very low levels of homogeneity in those areas where we have some synuresis and faults that are being picked up. Entropy, again, we've got lower levels of entropy in the homogeneous shelf, and then higher levels of entropy in the areas of synuresis and then in these faulted areas. So a great visualization for how much things are changing. Okay, so now I want to talk about the distance quadrant attribute, which is a newer AVO style attribute. It's actually been around for a couple of decades. It was used by Phillips back at the turn of the century, I guess. And we've picked this up at AASPI, working with some of the original creators of the DQ attribute, the distance quadrant attribute, because we found that it's been incredibly useful in helping us identify unclear layer boundaries, even distinguishing different fluid contacts, and giving us information about thickness in our packages. And so it's interesting, and it's very different than other attributes that we've used before, because it kind of transforms how we display the seismic data. And so just to give you a little bit about what this looks like, here we're looking at the VOLV data set, so the full stack amplitude data up in the North Sea. And I'm highlighting two areas here. So in pink, we've got a fluid contact. Up here in green, we've got lithologic variation. So there's actually a channel in this area, which we would have trouble just picking out from this amplitude data. Once we calculate DQ, it's much easier to see that there's something going on in this area, so we can kind of look through the data. It's kind of highlighting, hey, something different is going on here. We can look through it and then understand, exactly what's going on, which in this case is you've got a channelized shale in a channel, and there's a little bit of a slump block that you can even pick up. It's also been good for identifying some AVO or fluid contacts. So in this case, the oil-water contact, which is verified using a well. And what's great about this is you don't actually have to have the well data to run the DQ attributes. It just works on seismic, so the nears and the fars. And so here's another, the theta px, which is a transformation, just showing another DQ attribute. So we've got roughly a dozen DQ attributes that we're working on right now, and that have been showing a lot of promise. So one of my PhD students, has been working on this lately, and some of my master's students are starting to use DQ attributes in their machine learning algorithms. Just a couple weeks ago, Noor was showing me this kind of stichogram attribute, which is showing us the interfaces. It kind of helps with the calculation of isochron, so like a layer thickness and half isochron, which is showing us variability in the individual beds. What I like about the stichogram, and I'm curious about, is if we can use it maybe someday for more of an automated horizon tracking, since it's kind of noticing and improving those interfaces. All right, so just to talk about a little bit more about DQ, since it is a newer attribute. What it does is it converts partial near and far stack seismic traces into more quantitative measures that we can use. So you don't need to have any prior knowledge, so you don't need to know about the wavelets, the petrophysics, or much about the basin geology up front. And what's really cool, and I'm showing down here in the lower left-hand side, is that it mimics the porosity logs. So the output DQ shape we found using synthetic data, and we're proving up with real data. We've noticed that the shape of the DQ in a bed mimics changes in porosity. So we're really excited about this. It also kind of has a bit of an enhanced visualization. So just like acoustic impedance shows you the layers, DQ also converts the seismic from the wiggles into more of a blocked format. And it also, gives you information about all the data points. So you're not just focusing on peaks and troughs anymore. So when we look at this a little bit more, just to kind of explain really quickly how it works, what you're doing essentially is doing a phase rotation. And so in this case, I'm trying to show it with just 4 phase rotations. And so you've got to start with 0 phase trace, so that's kind of required. And then you do your phase rotations and assign quadrants. So in here we're working with 4 different quadrants based on the maximum value from each of the phase rotations, and then you kind of sum them together and you end up with your Q quadrant trace attribute. And to show an example of how this looks compared to AVO, in this case I'm showing just a wiggle of the near stack and then the far stack. Okay, so these circles, we've got a gas sand in the middle. The circles are the traditional method, the diamonds are the DQ trace. And so what you'll notice is in the gas sand, we're seeing the clear interfaces between the shale. We're also, kind of seeing the more blocky look of DQ. And when we look at this in a more traditional AVO cross-plot style, what I first want you to look at, because there's a lot going on here, is the circles. And so we've plotted here in pink, remember that's the gas sand, and then in blue and green, that's the shale above it. And so in AVO, so kind of an A-B type cross plot, you're not getting a lot of variation between the shales and the gas sand. And what DQ does is it performs a rotation. It optimizes it does a rotation and it pushes out the gas sands. What it ends up doing is it ends up pushing out the gas sands. In this case, so you can see the pink triangles or diamonds are more on the outside right here, and it helps differentiate fluids. So we have been very, very excited about this attribute. Okay, so just to kind of not finish up, but to move into the next part of this talk, I've talked about a lot of attributes. How do we visualize them? What type of, when we have like 20 attributes, what can we do with it? And so, of course, this is where machine learning comes into play. And so in my research group, we've been focusing on dozens of different machine learning attributes. So from dimension reductions like principal and independent component analyses and SOM, to unsupervised methods, semi-supervised methods, supervised methods like random forest, neural networks, like convolutional and probabilistic neural networks, UNet, GAN. So there's a lot that can be done. And so what I want to do is just wrap up with 3 quick case studies where we've been combining attributes and machine learning for CCUS case studies. So I'm going to start with the Decatur project in Illinois, move out to the Kevin Dome in Wyoming, and then move down to the Santos Basin offshore Brazil. So this is a paper, so all of these have been published except for the last one, but it was just accepted, so it's almost published. So this was a paper that was just published. It was led by my research partner, David Luba-Robles, looking looking at the detection of small offset faults in seismic data. So we're looking in an area where they're evaluating it for carbon capture. And what's been interesting in this part of the Illinois Basin is there's been a lot of microseismic events. And so we're using that microseismic data in order to, as kind of like a proxy for where these sub-resolution faults are located. And so here is just kind of a quick look at the area. So there's wells that have been drilled. Some of them have been injecting, doing carbon capture. We've got the microseismicity displayed here as the orange points, the well logs, and a lot of this injection has been happening in the Argenta Formation, and you can see also the Precambrian basement is mapped too. And so since these small-scale faults that we're not able to see really pose a risk for containment of the carbon, or may be very important to know about for geothermal evaluation, we need to have more advanced techniques for seismic, to find these subseismic faults. And so there's a lot more in this paper than I'm going to talk about, but some of the methods that I've talked about today that were applied in this study were spectral balancing, which helped improve the resolution. David also looked at broadband coherence, multispectral, doing a multispectral approach to kind of reveal some of those hidden lineaments, doing some frequency, so in case that's like frequency dependent fault visibility, to do that fault enhancement. And then also he used aberrancy, which is the attribute that I mentioned a bit earlier. And so just to show you one of the images from the result, on this left-hand side, we are looking at aberrancy, and you can see the opacity has been edited a little bit to look at faults in the more kind of like west and east direction. So in west, they're the green colors, and you can see that aberrancy is really able to pull out some of these lineaments, which end up corresponding fairly well with the microseismic. And so if this is used to aid in the fault enhancement, so this attribute is used to aid in the fault enhancement. And so, it's the same techniques we would use for, our traditional hydrocarbon, and they're very applicable to sustainable energy applications. The other reason I'm showing this study is because machine learning was not really used to detect, these subsurface features, these subsurface faults. So it's just, I always like to mention that machine learning is a great tool, but sometimes you don't particularly need it. So in the next one that I'm moving to, we did use machine learning. So this was some work done by one of my master's students in the Kevin Dome area. Again, it's been published in the Leading Edge, where she was looking at an area that was under investigation for carbon capture, utilization, and storage, using both multispectral attributes, and aberrancy is one of those. And then she used a machine learning method called GTM, generative topographic mapping, to help see these previously unseen fault networks. So as we look at this, just a little background. Here we've got the Kevin Dome, a couple of different horizons that have been picked out. So in the upper Duperow Formation, the upper portion, the mid portion, and then the lower portion. And just looking at a comparison between the broadband coherence in this upper part and kind of the grayscale, and then the multispectral coherence, where she focused in around 63, 54, and 71 hertz, and she's using that RGB blending. And so some of the features that are pointed out with these arrows are some previously unseen kind of karstic features and potential fault lineaments in this carbonate reservoir. Curvature and aberrancy were also looked at as attributes. So you can see in curvature that it is able to pick out now, better than just the broadband coherence, some of these features and lineaments, and aberrancy does a spectacular job of picking out even more lineations. So if you're going to be injecting in the subsurface, you want to properly risk your reservoir. And so I'm a big fan of recommending that folks use aberrancy for that risking. Of course, we're investigating machine learning methods, and so this is one of the methods she applied in the paper. The paper has other ones too that you can go and look at. But in this case, she took several of the different attributes, combined them in this unsupervised classification method to create more of like one image where you're looking at multiple attributes at once. So you can see a lot of those lineations that were apparent in some of the attributes, but not all of them, show up very clearly. And they also kind of agree with the stress regimes and what's known from well data in the Kevin Dome area. All right, so I'm going to wrap up with one last case study. This one, like I mentioned before, it was just accepted by interpretation, so I've got to change the slide apparently. But it's part of a PhD thesis that Marcus Maas worked on. And so the first two papers that were looking at attributes and unsupervised methods were accepted, and then the third one, which I'm showing you the results of today, was accepted. So the first two are published, the last one was accepted. Okay, so we're working in this area. It's the southeastern Brazil, so we're offshore. We have some data from Petrobras. They have this Mero field, which has a lot of wells, 3D seismic. It's well developed by Petrobras. And what we're looking at in this case is using attributes and then transfer learning to kind of apply what we know about the Mero field and see if we can get accurate results in the Lapa and Bacalhau fields. So what I want to just pause and say right here is that we're training only with Mero, and then we're taking the results of that training and applying it to Lapa and Bacalhau. So it's kind of a really unique study trying to see how far we can take machine learning. And so just a quick overview of the method. The first thing that we always do with machine learning is we try to validate the reservoir models. So in this case, I had mentioned he had done unsupervised and supervised classification from SOM methods to random forest, and then used PCA, principal component analysis, and to understand which attributes mattered, and some exploratory data analysis also for choosing which attributes to run in the new fields based on what he saw in Mero. And then that transfer learning is applied, and we've got some models which we can link to flow capacity. So here's maps of the three different fields. So the Mero, the Bacalhau, and the Lapa field. So just mapped on the top horizon, and this is for the Barra Velha formation, which is the formation of interest. You can see that there are wells in all three of these areas. So the wells are used not in the training for Bacalhau and Lapa, but rather for validation. So to see if that transform learning did work. Here's kind of an idea of the gross depositional environment. So again, they're not quite the same. They're all in the same basin. You can see that the Mero field, which is the original field trained on, there's a lot of buildups and mounds. There's high energy platforms, so in that blue color, which we don't see in Bacalhau. In Bacalhau, there's some volcanoclastics, which aren't in the original training data set of the Mero field, and not in the Lapa field either. So some variation between these fields in this formation. So Marcus had looked at the Mero field and seen which attributes mattered the most, so the ones that were most important for the random forest classification, and then used these same attributes and calculated them on the seismic for Bacalhau and Lapa field. And so just to kind of like go to some of the results, what is great about this study is we had a lot of information about flow capacity, so how well these reservoirs were producing. And so in this case, there were a couple of wells that were saved, so this is the Mero field, for blind testing. And what he found is that the algorithm, the machine learning algorithm, and these attribute combinations could identify hyperflow geobodies. So you can pick these out and then target them. So now moving into transfer learning, I'm just going to show with the Bacalhau a couple of images before I wrap up. He used SOM clustering to get these flow capacity predictions using the Marrow parameters. So here we're looking at the Hilbert transform of the input amplitude kind of shown in a grayscale. There are two wells that we're showing just kind of for validation, but these weren't in the algorithm itself. After SOM was run, comparing it to what we saw in Marrow field, so using the Marrow combination of attributes, the higher energy areas were similarly kind of detected in these blue colors and the purplish colors, so kind of great transfer of results. And then doing a flow capacity prediction using the same parameters in the random forest regression that was used in Marrow. We've got ideas of where the higher flow capacity is, so those purple colors in this Bacalhau field. And that, of course, can be translated into geobodies, and using the wells as validation, there was really good alignment. So we were very excited to kind of show up that transfer learning method. All right, so let me wrap up, last slide, with some key takeaways. So as I've kind of talked about, many of the methods that we've developed for traditional hydrocarbon exploration are great for this energy addition, expansion, and sustainability. So as we move to add in new energy types, I want to encourage all of you all to kind of, stick with some of the classics, some of the methods that you've been learning, because reservoir characterization is, to some extent, reservoir characterization. I also want to encourage you to think about using seismic attributes more. So there's a lot of them out there that can help you see more in the seismic data. Of course, you don't want to run hundreds of attributes, but rather be a little bit picky in choosing which ones you need to see, or which attributes help you see what you need to see. And then, of course, combining attributes can provide you with a ton of information that exceeds what you'll see in one individual attribute by itself. And so that's where machine learning comes into play, and other statistical methods. There's many of them out there that can help you leverage these seismic attributes to better classify your reservoirs, whether it's rock properties or facies, and help you in your drilling operations. And so I want to encourage you to try out a new attribute. Maybe I mentioned one that you hadn't heard of before. And so I wanted to point you to the AASPI website, where we have a ton of different videos and documentation with the math and the theory behind all of these that you can dig into more. So just kind of showing here on our website, I've got videos of different lengths from 2 to 10 to 20 minutes talking about many of the different attributes that we use all the time. So might be good for some of your morning coffee breaks. And of course, I have a lot of people to thank, like Kurt Marfer and David Lubo are like kind of my partners in crime in a sense, working with me to get the most that we can out of our seismic data at the University of Oklahoma. And then I showed different case studies from several students, and of course all my AASPI researchers, and all of our sponsors are incredibly helpful in helping me fund the students who do a lot of this research. So there's a lot more information from our webpage to our YouTube channel, and then on LinkedIn we're always trying to put out fun little updates, kind of encourage you to try out some different seismic attributes. So thank you very much for attending, and I'm happy to answer questions. And of course, this is going on the YouTube channel, so you could post questions below.